This is a basic tutorial on how to interpret proton NMR spectra. On the left-hand side here, I have a model of ethyl crotonate. Ethyl crotonate has a variety of carbon and proton, different carbons and protons that makes this for a nice tutorial molecule. Note that my molecule here does have a double bond right here. This is a double bond, and then this is a carbonyl. But my model viewer doesn't show double bonds very well. But if you notice that we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got 10 protons, 10 hydrogens in this molecule. And we want to look at the proton spectrum to see if we can identify those different hydrogens. On the right-hand side here, I have the FID, or the free induction decay, from a proton NMR experiment that I've collected. This is the Joule Delta software that we use for our NMR. I'm going to click on the 1H button to set up the general parameters for processing, and hit the process, and there we go. We've got a proton spectrum down in the bottom right-hand corner here. If you have your the Delta software, notice how my cursor looks like a little integral sign. That's because the cursor is currently on the integral feature. If I hold down the Shift key, it changes to a magnifying glass. And the magnifying glass allows me to zoom into different regions. So I'm going to use that, click in the gray area so that it just magnifies in the X direction, and that brings up the signal here. I can do the same thing on the Y axis if I want to zoom in, and I can zoom in multiple times. If I hit the backspace key, there's sort of an undo on the zooms. And so we see 1, 2, 3, 4, 5. 5 different signals in our NMR spectrum. If we take a look at our molecule here, we see that we've got one set of hydrogens on this CH3 group here, that those are equivalent. We've got this set of hydrogens, which are on the CH2 group next to an oxygen, and those two are equivalent. We've got this CH3 group on the other end of the molecule. They are equivalent to one another. We've got this one CH group. This hydrogen is unique, as is this hydrogen here. So we had 1, 2, 3, 4, 5. 5 different sets of hydrogens corresponding to the 1, 2, 3, 4, 5 different signals that we observe in the ethyl crotonate spectrum. So the question is, which ones belong to which? The two things that the two features that we have to look for in a proton NMR spectrum are the areas of the curves, areas of the peaks, and the splitting patterns. I'm going to zoom into this region right here just to start with. Integrate just this one and this one. So notice how the area underneath these two curves are equal to one another. That means that the number of protons that correspond to this signal is the same number of protons as it corresponds to this signal. That means if this actually is one proton, then this has to be one proton, 2 protons, 2 protons, 3, and 3. The area underneath the curve does not tell us the absolute number of protons. It tells us the relative number of protons. So if we take a look at our spectrum, or at our molecule over here, we have a set of 3 and a set of 3 chemically equivalent hydrogens, and then we have a set of 1, and both of those have ratios of 1 to 1. We can definitely rule out the CH2 group because there's no other feature in ethyl crotonate that also has 2 equivalent hydrogens. So we know that these two do not match up with the CH2 group. If we take a look at the rest of our spectrum here, we see that this feature integrates for a small number, about 0.3. This one is around 0.25. And then this one here is around 0.67. So it looks as if we've got the largest peaks on the right, a middle-sized peak in the middle, and two smaller sets of peaks in the left-hand side. That allows us to propose that the two features between chemical shifts 1 and 2 ppm belong to the two groups with the largest number of protons, so these two CH3 groups. The one in the middle here likely corresponds to the CH2 group, and then these two at the end correspond to these two CH groups. Right there. Okay, so let's go back and take a look at the CH3 groups one more time. And the other very important feature in NMR spectra is the splitting pattern. Notice how this particular set of peaks is split into 3 subpeaks with a ratio. Turns out the ratio is 1 to 2 to 1. And we can prove that. Let's go ahead and get rid of this. Oops. And I'm just going to integrate each one of these individually. There. We have 1 to, oops. Oh, that's because I did a bad job with integrating. There we are, 1 to 2 to 1. So the ratio 1 to 2 to 1. We'll talk about. You'll hear talk about Pascal's triangle, which explains the relative heights of these peaks. But for starters, if you see a pattern that has 3 peaks, then that corresponds to a neighbor with 2 equivalent hydrogen atoms, or 2 equivalent atoms in the more general case. So we said because of the area of this curve, it corresponds to one of the CH3 groups. And if we look at the splitting pattern, that means its nearest neighbor has 2 equivalent hydrogens on it. So let's take a look at our molecule here. And we see there are 2 CH3 groups, but it's this CH3 group that actually has 2 nearest neighbors. So we can unambiguously assign the peak at 1.2 ppm as belonging to this CH3 group that has been highlighted. Therefore, the one at the other end, we can actually make a prediction here. If the nearest neighbor, if there's only one nearest neighbor, then we can predict what the shape of this set of peaks should be. One neighbor plus 1, we should see a doublet here. Let's see if that's true. We look at the other peaks, and we actually see a doublet of doublets, and that's because of the impurities, or possibly because of longer range coupling. We'll discuss that in later videos. But we see 2 main features here. We see 2 peaks, and this is consistent, although granted, because we see some additional features here, it's not as unambiguous as the first one. We have what is suggestive that this CH3 group is the peak that shows up at 1.83. Okay. Let's take a look at our CH2 group. CH2 group has a neighbor with 3 equivalent hydrogens in it. 3 plus 1 is 4, so we should expect this signal to have a set of 4 hydrogens, a set of 4 peaks. 1, 2, 3, 4. And this one looks correct. 1, 2, 3, 4. And these should be roughly in a 1 to 3 to 3 to 1 ratio. Great. So now what we're left, we've identified all of the hydrogens that are in green, and we're left with assigning the 2 CH groups here. Now if we take a close look at the CH groups, let's start with this one. This CH group only has one nearest neighbor. So we would expect that this CH group, or this particular hydrogen, would be split into a doublet, because it's got one nearest neighbor with one equivalent hydrogen. 1 plus 1 is 2. If we look at the peak at around 5.8, we do see 2 features here. Now notice it is, again, we see some additional fine structure, and that is due to the fact that it's not just the nearest neighbors, but the farther away neighbors will contribute to the splitting pattern that we see. But we see 2 general features, and so we can assign the peak system at 5.8 to that one hydrogen. Likewise, oops, there we are. If we take a look at this peak here, this hydrogen, we see that it's got one neighbor, which is split, which is going to split it into a doublet, and then another set of neighbors, which is going to split into a set of 4 peaks. And we look at here, and we can see that that's probably what's happening. 1, 1, 1, 1. So that's there's a 1 to 3 to 3 to 1 ratio right here, and then there's a 1 to 3 to 3 to 1 ratio here. And remember, that's indicative of a hydrogen that is split by 3 neighbors. And then these 2 features, we see 2 of these, and that is indicative of being split by a single nearest neighbor. Now you may ask, but wait a minute, if we take a closer look over here, isn't that the same thing that we see? We see 1 to 3 to 3 to 1, 1 to 3 to 3 to 1, and it's split by nearest neighbors. And you're absolutely correct. Both of these features, both of these sets of peaks, have very similar patterns to them. The difference here is in what we call the coupling constants. Now the coupling constant is the distance between the individual peaks in the pattern. For example, if we take a look and measure, let's go ahead and measure the distance between these 2 here. I'm going to change the units to hertz, standard. And we see that the difference here is around 1.8 hertz. Let's look at the difference between these 2. 1.6 hertz. Let's look at the difference between these 2. 1.8 hertz. So within experimental error, the separation between these is around 1.8 hertz. Let's look at this one here. 1.5 hertz. 1.89 hertz, 2 hertz, that's probably a little bit big, but again, within error, we're looking at around 1.8 to about 2 hertz. Now, what about the separation between these two larger features? Let's go to the middle here to the middle of here. And that's around 15 hertz. Okay, so the closer the neighbors are, the larger the interaction is going to be. In general, there are going to be exceptions, but in general, the closer the interaction, the larger the separation between the peaks. Let's go ahead and do the same analysis for the ones over here. Clearly, the separations are more similar. Let's see. So that one is roughly 7. That one's roughly 7. That's roughly 7. Notice how it's this actual coupling constant allows me to say that the pattern 1, 3, 3, 1, this is the 1 in that pattern and not this one here, because the separation between these two is only around 1.3 hertz, and that doesn't match the separation, the coupling constant separation here. Let's look at the second pattern. There's a 7 hertz. There's a 7 hertz, and again, there's around a 7 hertz. So that means that suggests here we have a 7 hertz coupling constant, whereas here, what were these again? Oops, I lost my. Let's pick it up. There we are. These are all small, with around 1.6 hertz. So these are much smaller, suggesting that that the neighbors doing this splitting are farther away than the neighbors that are doing this splitting here. Lastly, let's go ahead and measure the middle of this feature to the middle of this feature. And we get around 15 hertz. So that means that the distance between this CH group and its neighbor is likely the same as the distance between this CH group and its neighbor, because those splitting constants are the same. So the splitting of this doublet, and that sort of makes sense. If we take a look at these two, oops, which one is it? There we are. At these two hydrogens, when this neighbor is talking to this atom, the splitting should be the same as if this neighbor is talking to this atom, because it's mirror images of one another. So that 15 hertz splitting is due to these two talking to one another. Because the splitting, the CH3 splitting in this feature is smaller than it is in this feature, then that suggests that the distance between the CH and the CH3 in this feature is greater than it is in here. And so it's those investigation of the coupling constants that allows us to differentiate between these two features. When we look at the two-dimensional cozy experiments, we are going to be able to analyze that this feature in a lot easier fashion, but we'll save that for a new tutorial. To summarize, what we've learned today is that the proton spectrum can tell us an awful lot about the structure of a molecule if we pay attention to the number of chemically equivalent protons in the spectrum. The splitting tells us something about its nearest neighbors, and the integrals, or the area underneath the curves, tells us something about the relative number of protons between those two signals. That's the important take-home message today.